In this chapter, we will include scattering from impurities that makes Nordheim's rule, and how to add different scattering mechanisms together, which uses Mathiessen's rule. In the figure, we see resistivity plotted as a function of temperature for a variety of different metals. In general, we see resistivity increasing with temperature, as explained by the theory described in the previous section. The thermal scattering we discussed earlier predicts a resistivity which rises with temperature linearly, which on a log-log plot has a slope of 1. The experimental resistivity values of pure metals generally follows this trend, which validates the physical principles we used. However, because accurate values are needed for engineering electronic devices, modified formulas with tabulated parameters are often used. The most striking differences are seen in these metallic alloys, which have very high resistivities and very little temperature dependence. This is because these are not pure elements, but instead random alloys of a variety of different elements. The random arrangement of these atoms leads to a different form of scattering, which we will call impurity scattering. Consider again an electron traveling in a crystalline solid. We will learn from quantum mechanics that an electron traveling in a perfect crystal, where atoms are not moving, will conduct with no resistance. However, if the atoms are moving such that there's a distortion in the lattice, then the electrons will scatter off the atoms. Similarly, if there is distortion in the lattice, such as due to an impurity, the electron will scatter off this impurity. This impurity could be a larger atom or a smaller atom than the normal periodic lattice. Also, an atom with a different charge state will interact strongly with the charged electron and scatter also very strongly. The stronger the impurity atom will scatter will make its effective cross-section, or scattering cross-section S that we discussed previously, large. For impurity scattering then, we have the mean free time of scattering is inversely proportional to the effective scattering cross-section, the mean electron speed, and the concentration of these impurities. Keeping in mind that the scattering cross-section of the impurity has more to do with the strength of its interaction with the charged electron than its physical size. So for now, we will think of it as a fitting constant. Also, notice that for impurity scattering, we have the concentration of impurities, which is a real quantity we can change in a material, unlike the thermal scattering, which we discussed previously, where every atom in the system is vibrating. So now we have described two types of electron scattering in a metal that leads to electrical resistance, thermal scattering and the impurity scattering. In general, both types of scattering will happen in a crystal, and so we will need to know whether we can simply add them to find the total resistance of that metal. Using probability theory for these random scattering events, we can show that the inverse of this total scattering rate is the sum of the individual scattering rates from the thermal scattering and the impurity scattering. This rule for adding scattering processes together is known as Mathiessen's rule. If we now multiply both sides of this equation by the mass, the electron density, and E squared, we can convert these inverse relaxation times to resistivities using the relationship that the resistivity equals m divided by ne squared tau. In this way, we can then use Mathiessen's rule for how to sum these relaxation times to show that the total resistance is simply the sum of the individual resistance, as if we were combining these resistors in series. Here we see a plot of resistivity as a function of temperature from very low temperatures up to about room temperature for a number of typical metals. Pure copper with very large grains has very, very low resistance, and that resistance rises such that around room temperature it rises linearly as expected from our model for thermal scattering. Above this line are data of the resistivities of copper with a small amount of nickel. Notice that the resistivities look like they are simply shifted up by a constant amount, and that this constant amount increases as the concentration of the nickel impurity increases. Thus, we would expect that the resistivities of metals with small amounts of impurities, such as nickel, would very well agree with our linear plus a constant model by including our thermal scattering plus our impurity scattering together. Also shown in this plot are the resistivities of materials that are deformed, and notice that these also look like they're essentially shifted up from the pure copper resistivity. Because these resistivities have the same slope, we would expect they would have the same types of atoms doing thermal scattering, and that this constant shift has to do with impurities, perhaps another mechanism of impurities. Well, these are for deformed metals, and so these deformed metals appear to be also increasing the resistivity in a constant way, as if they're adding impurities. Well, we know that when we deform a material, we may not be adding necessarily impurities, but we are adding dislocations, perhaps producing smaller grains, and each of these can also scatter the electrons. To characterize and compare the resistivity of various metals, we like to first tabulate the room temperature value of the resistivity, and then perhaps a small correction factor due to the linear increase in resistivity with temperature. The temperature coefficient of resistivity, written here as alpha sub 0, is then the temperature derivative of the resistivity divided by the room temperature resistivity, so that we can describe the temperature dependence in the equation given here. Notice that because 1 is unitless, alpha sub 0 should have units of inverse temperature. Recall that we saw that the resistivity of pure copper was quite small, but increases rapidly as we add impurities such as nickel. Also recall that the resistivity increase is roughly proportional to the amount of nickel at small concentrations of nickel. Copper-nickel alloys are a good system to study impurity scattering because copper and nickel form a complete solid solution with the same structure from 100% copper to 100% nickel. With such a solid solution, then, we can see that the resistivity indeed rises linearly, but then reaches a peak and drops also linearly at the other end. Well, at the pure nickel end, we can think of the copper as being the impurity, and so we would expect a linear increase in resistivity due to the impurity of copper now in nickel. For the full system, then, we would expect something that looks more like an inverted parabola, where we have linear increase in resistivity at both ends that reaches a maximum somewhere in the middle. This inverted parabola is nicely given by Nordheim's rule for solid solutions. Here we have the resistivity due to scattering of electrons from the impurities equals a constant known as the Nordheim coefficient times the atomic fraction as x times 1 minus x. When the atomic fraction is very small, we can ignore this x, making the resistivity due to impurities simply a constant times the atomic fraction. When x is close to 1, 1 minus x becomes the atomic fraction of the impurity, and so we have the resistivity due to scattering of the impurities is again a constant times 1 times the atomic fraction of impurities. In the middle region, when x is around a half, we indeed get the inverted parabola as we hoped. Using Mathiessen's rule, we can find the resistivity of our material for both scattering mechanisms combined by simply summing the components of resistivity from each mechanism. Here we have the resistivity of the matrix, which includes the thermal scattering, so that we have the temperature-dependent term plus a constant term due to other defects such as dislocations formed during work hardening, and then the impurity scattering due to the solid solution alloy, where we use Nordheim's rule.